So it's my pleasure to welcome Enrique for our Dynamical Systems seminar, and he will be talking about reaction diffusion in social and biological sciences dynamics and ResNet control. Yeah, thank you.
Okay, thank you, Boumediene, for giving us this opportunity. I will be presenting the work we have been doing recently in collaboration with a number of colleagues in our team, in particular with Domènec Ruiz, who he was trained in Barcelona and then got a master in L'Aquila in Italy, and he has been working with us now for 3 years in our team. He's about to finish the PhD thesis, and to a large extent, the work I am presenting is what he has been doing in his PhD. So, as you know, when I was discussing with Boumediene about what topic I should speak on, Boumediene told me, well, we don't really do control, right? So, but in fact, everyone does control, right? So, and precisely the aim of my lecture is to show you that oftentimes, even if we don't realize it, the way problems are formulated, the problems arise either in nature, in social sciences, or in technology, there is always some control theoretical aspect that is hidden, and that even if we really are not experts on that, we use to handle it in a way or another. So, in fact, when you look how the theory of applied mathematics developed and the point we are stand now, we could say that to a large extent, applied mathematics is about modeling, analysis, of course, computer simulation and numerical analysis, and I will say also control, right? Control, design, parameter identification, these are topics that are hard to distinguish very often, right? Actually, in order to illustrate the possible directions of activity in this area and some of our interests, we have developed this DICON blog, right? DICON is our European Research Council Advanced Grant, Dynamic Control, that has been now ongoing for 4 years. And in that web page, you will find that in our blog, you will find several, articles, posts with different control applications, different modeling, and different mathematical and computational techniques that we have developed to tackle them, right? So our interest in this topic of reaction diffusion models arising in biology and social sciences arose from a conversation with a colleague, José Ramón Uriarte. He's a professor in economics in the University of Basque Country in Bilbao. And he was asking me, Basque Country is a bilingual region where the majority speaks Spanish, and then there is a minority of Basque-speaking population. And he was, curious about what will be the mathematical modeling of this kind of bilingual dynamical societies, right? And in particular, how when you meet a person in the street in a bilingual, country, how these people or these groups of people decide to either talk in one language, in this case, the majority language, or the other, right? And this is actually something we all experience, right? When you are traveling a war, abroad, maybe very far, and you are coming back, and then you see people in the airport that look familiar, and or you wonder whether they are from your country or from your region. You observe these people and you try to identify, some peculiarities, right, in order to figure out whether they are actually from your own region or not, right? So, of course, there are some signs that are not so strong. Like, for instance, if you see someone with a messy T-shirt, it doesn't necessarily mean that this person is born in Barcelona, right? But if you see that this person is reading a local newspaper in your own language, then you will consider that as being a clear indication that this person is actually from your own country and able to speak in your mother tongue, right? Okay, so the modeling that Jose Ramon Uriarte and collaborators have did on this topic was based on game theoretical, say, modeling techniques. And of course, our approach was more based on partial differential equations, dynamical systems. And when trying to, say, address this topic, the first thing we had to somehow discuss was, well, how do you actually model social dynamics when you are discussing about people, individuals, population meeting in a multicultural, say, context and choosing to, you know, to use one language or another as a communication tool. And then there are, of course, different, say, levels of modeling you can employ. You could employ ordinary differential equations, stochastic differential equations. You could use PDEs, mean field equations, kinetic models, maybe networks also, because society are built in networks. We are all commuting and not only communicating, but the way we meet, you know, the opportunities we have to meet people are built on our own physical motion along networks between cities, transportation, and so on. So there are many, many different scales in which this model can be modeled, right? As I mentioned before, in our ERC Advanced Grant icon, we have a blog. We have also developed this computational toolbox based on MATLAB. You are also welcome to have a look to this. This is, of course, open access, and you can employ it if you wish in order to tackle, you know, control-oriented problems, right? So what we did in our work was, you know, begin by a classical, say, model, right? A bistable reaction-diffusion model in which, I mean, the same can be written in multi-space dimensions, right? But this is basically a reaction-diffusion problem for a population which is living in a one-dimensional domain, right? There is diffusion of, you know, communication, interaction, you know, gene propagation, right? Through this diffusive operator on the left-hand side of the equation. And then on the right-hand side, you have the typical nonlinearity, which is this bistable nonlinearity, right? In which you separate the population, which is, you know, in between 0 and 1. And you could think that y equals 0 is one type of population and y equal 1 is another population. It could be in this bilingual game. It could be people that are, say, better, you know, behaving one language and one people that rather prefer the other one. Or it could be the monolinguals in a, say, bilingual environment. I mean, you can think on different kind of population traits, right? This is a very classical model that has been very much employed in different applications in mathematical biology and in social sciences. And one of the features in this model is this theta, you know, Ali threshold parameter, this Ali threshold parameter, right? As you see in the nonlinearity is negative between 0 and 1, right? And it's positive between, say, theta, sorry, is negative between 0 and theta, and then it's positive between theta and 1, right? So what means is that when, you know, y is greater than theta, the nonlinearity is positive, then you are feeding the system, right? While when the value of the solution y is between 0 and theta is small, then the nonlinearity is negative, and then you are pushing down, right? So this is typically a situation in which the two, say, populations are competing, right? And the nonlinearity is, you know, pushing either towards or towards the other, right? As I said, this is a classical model in social and biological dynamics. And, you know, even if in principle, this model is used often out of the context of control, right? Actually, you see immediately already in this model that this parameter theta, this Ali threshold parameter, can also play the role of a control, right? Because depending on whether you make theta to be, say, smaller or larger, you see that you are enlarging or compressing the range of values of y where the nonlinearity is pushing down or is pushing up, right? So theta equal to, say, smaller or larger is a way in which you can regulate the behavior of this dynamical system. And this is actually something that is used, for instance, in the propagation of diseases. In pandemics, this will be, for instance, the vaccination effects, right? So, with theta, if you vaccinate population, then you will make more, a bigger percentage of the population to be immune, and this will correspond, for instance, to increase the value of this parameter, so that theta, so that a larger range of the population lives within this set in which the nonlinearity is pushing down, and therefore the nonlinearity is helping the decay of the pandemics. The same is often used in the context of the avoidance of invasions of insects, for instance, by feeding in this population of invading mosquitoes, for instance, sterile mosquitoes, in which you increase the volume of the population, keep the fertile population fixed. This means that overall the rate of reproduction of this population diminishes, and in this way you push the extinction of this species. So even if you are not doing control, just by playing with this parameter, you can see that the dynamical behavior of this system changes, and this can indeed, this modification of the dynamical properties of the system can be interpreted in terms of control, right? So actually, when you look to this nonlinear partial differential equation, the state y represents, the percentage of population with a given, say, gene between 0 and 1, or a typical behavior if we are talking about bilingualism between 0 and 1, right? When you look to what kind of solutions you can find, of course, there are three trivial solutions, right? Are the constant solution 0, theta, and 1. By constant, I mean independent of space and time, right? Because if the solution y is constant, then the partial differential operator on the left vanishes, right? Both the time derivative and the space derivative of this constant will be 0, right? But on the other hand, of course, the nonlinearity also vanishes, right, on the right-hand side, right? And therefore, this is a steady-state solution. Well, these are very natural steady-state solutions of this problem, right? But there are some other very interesting equations or solutions that arise for this equation, are the so-called traveling wave solutions, right? I think the first one to compute the solutions, the traveling wave solutions for this kind of models was Kolmogorov, right? So what is a traveling wave solution? Well, a traveling wave solution is a solution y, which is dynamic, right? Which is evolving in time, which depends on x and t, but depends on x and t in a simplified manner, in the sense that y is simply a given profile, capital U, which is being transported, right, along, say, the xt plane, right, with a given velocity c, right? This is a kind of surprising effect, right? Because when you look to this equation, in principle, you don't see any kind of transport phenomena arising in this model, right? This model is the accumulation of two effects. One is diffusion, and diffusion, as you know, is just the Gaussian diffusion. It's purely central or radial, symmetric. And then there is the nonlinearity, which is pushing up and down the population depending on the amplitude of y. But there is no effect in this model that anticipates that there will be any kind of transport of convective effect. There is no wind pushing in this model in principle. Despite of this, there are these kind of traveling wave solutions. Actually, these traveling wave solutions, as you can see here down, they are explicit, they can be computed as just an exponential transition between 1 and 0, right, which are the two extremal steady states, right? So the traveling wave is just an exponential profile moving from 1 to 0 or from 1 or 0 to 1, right? Of course, the equation is symmetric with respect to the reflections on the x-axis, so you can write it down in both ways, either going from 0 to 1 or from 1 to 0, right? You just symmetrize the solution and you have it. But of course, what is interesting in this problem is that, the propagation, the velocity of propagation c of this traveling wave is something that depends on the value of the parameter theta, right? Actually, when you look to the value z in this in the last line, you can normalize this amplification factor if you wish to 1, and then when you look to the sign of this velocity of propagation, you see that for theta is smaller than 1/2, as in this drawing, right? When theta is smaller than 1/2, the nonlinearity is more positive than negative. It means that you are rather pushing up rather than pushing down more frequently. In that sense, the value 1 of the solution is favorized, and this is actually what you see, right? You will see in that case that the traveling wave, which is represented here in blue, right, will move to the left, and in the end it will be like with like a wave that will invade the whole domain, so that the whole domain will have the tendency to go to 1. This is why this model is so much employed in mathematical biology, in social sciences, also in combustion theory, right? This is also a model for the propagation of fire, right? So the fire simply propagates, right? Of course, in case there is wind, the fire will propagate faster. But in practice, you see the fire can burn and will propagate even in the absence of wind. How it may happen, Ron? This is a very interesting question. How it may happen that in a model in which, in principle, there is no any term that allows us to anticipate this transport or convective phenomena, how it may happen that this actually arises. So, in fact, this is something that we all know. I mean, it's the phenomenon of, in Spanish, we call it la ola, or the wave. It's like, people, observing soccer in a football stadium, right? So everyone is sitting, but after some time, a group of people decided to leave, right, to stand. And then this is a jest that the neighbors, imitate. And in this way, this generates a kind of traveling wave profile or front propagating. How can we see that from a mathematical perspective? Well, possibly the simplest way of understanding what's going on is just think that by splitting, if you have a dynamical system in which two operators are generating the dynamics, one is this diffusion operator associated to the Laplacian, and the other one is the nonlinearity, right? We can decompose this dynamic into two dynamics. One is the ODE and the other one is the diffusion. And then by using domain decomposition or standard splitting techniques, we know that the overall dynamics will be generated by just, according to Lee, splitting lemma, it will be just the result of passing to the limit on an alternating resolution on one equation and the other, right? You see that if you solve one and then the other and then go back again, this is what you see in the video, right? You see that indeed, eventually, the motion arises, right? And in order to explain you why this motion arises, let me go back to the origin. I have taken this initial datum, for the distribution of population. It's a population which is, is kind of a segregation situation where the population close to 0 is living to the left, and the population close to 1 is living to the right. Those that speak one language live to the left. Those that speak the other language live on the right, right? There is diffusion. Diffusion means there will be mixing, and this mixing will somehow enhance this, nice, exponentially smooth transition, right? But on the other hand, there is the nonlinearity. the nonlinearity in this case, theta, is smaller than 1/2, right? It will be, maybe in this case, I think in this drawing is 1/3, is 0.3 something, right? It's 1/3. So this means, as I have mentioned before, that in our nonlinearity, the value 1, right, has the tendency to absorb more population than the left, right? And this is actually what happens, right? So this introduces a cut on the population at this level, and this produces the shift of the center of gravity that rather than being, you know, at this half point, it will shift here to the left, and then the diffusion will simply reset the center of gravity, you know, whenever it arises to that point. And this is actually what you see. You see how the impact of, you know, the nonlinearity pushing in an asymmetric manner towards 0 and towards 1, plus the tendency of the diffusion to symmetrize the dynamics, makes that eventually, you know, the wave propagates to the left, so that eventually the one population, the one that is dominant, the one that is favorized, you know, invades the whole region, right? This is why, you know, of course we know, I mean, this is according to intuition and also to our experience, but from a mathematical perspective, this is a way to justify that, I mean, if you want to equilibrate things in social life, whatever the, you know, the context is, you know, some measures in order to somehow generate some diversity balance, you know, some support to the minorities, is something that is absolutely needed in case you want to escape to this boring situation in which simply the majority invades everything and the diversity simply, you know, evaporates, right? Okay. Now, this topic, as I said, started with Kolmogorov, has been a classical in combustion theory, in mathematical biology, you know, interacting species, in gen flow, you know, genetic propagation, population dynamics, infectious diseases, the propagation of neural pulses, combustion theory. As I said, there is a wide range of potential applications of these kind of models. From a mathematical perspective, it was in the 70s when, say, the pioneering work in this area was done. And in particular, there are two papers. One is by Aronson Weinberger and the other one by Five and MacLeod, where, you know, they do the basic analysis of the, say, dynamical system properties of these systems. And in particular, they discuss, you know, the existence of these traveling wave solutions, right, and their stability properties. I should say that, of course, these explicit computations in which, according to Kolmogorov, you can explicitly compute the traveling wave profile as being, you know, an exponential transition between the two, say, stable steady state 0 and 1, theta, the intermediate one, being the unstable steady state. This explicit solution only arises for this very particular cubic nonlinearity, but part of the work of, say, Aronson, Weinberger, Five, MacLeod, and many authors since then, has been to show that this is something which is quite generic. Whenever you have this kind of bistable nonlinearities, even if you don't have this very explicit cubic, say, behavior, you will encounter this kind of traveling wave solutions. And to a large extent, these traveling wave solutions are the universal attractors of the dynamics, right? Okay, so then this is just a very brief introduction to these kind of models, the reaction diffusion models for population dynamics in sociological and biological sciences, traveling wave solutions, the stability properties of these traveling waves. And as I said, well, when you see this, you say, well, there is nothing about control here, right? Because you are simply talking about the dynamical system, particular solutions, and the possible asymptotic behavior and the attractiveness, right? So this is just qualitative properties of PDEs. There is no control on this. But in fact, there is, right? Because as I have shown you before, right, even if the profile of the traveling wave solution is independent of the parameter theta, you see how in the last line where we draw the velocity of propagation c as a function of the parameter theta, you see that, for instance, when you switch theta from being less than 1/2 to being larger than 1/2, you see that the sign of this velocity of propagation parameter c changes from negative to positive, and then by doing that, you succeed on making this traveling wave front that was before propagating, to the left, as in this video. If you change the parameter theta from being less than 1/2, like in this drawing 1/3, to being greater than 1/2, then you will succeed that this traveling wave will propagate in the opposite direction, right? And this will actually, when you succeed on making this traveling wave to propagate in the opposite direction, now you will see that rather than being one who invades the whole universe, it will be the zero one that is invading, the space domain, right? And this is actually what happens also, in social networks very often, and which also happens in democratic countries where people vote, and then you see how the voting in one election can be pushing the election towards one side, and then after a few years how the pendulum can go back, and then the people's opinion can push, say, power in the other directions. Actually, we were discussing with Boumediene that 2 days ago there was the voting of the new constitution in Algeria, and today I think there are also important elections that are ongoing in the United States, right? And the question is precisely whether, for instance, the question in the United States is whether the parameter theta has switched from being less than 1/2 to being larger than 1/2, or whether maybe by some, say, a small, say, margin, the sign of the parameter theta persists, in which case there will not be a swapping, a switching, on the government, right? So then you see that, in fact, if you have a good understanding of the dynamical properties of a system, in some sense, you are already ready to do control, or you are doing control, right? And this is actually what we often do when we are offered a new toy, right? So if you receive, for Christmas as a present, a drone, right? This drone will come with, say, 500 pages of instructions. So there are two ways you can play with that. You can read all these instructions before you start playing with your drone, or you will rather do as this kid is doing in this picture. You just put the batteries on, turn it on, and start playing with the buttons, right, and the different actuators, right, to see how this drone flies, and with this you will learn, right? So normally, we do control in our, say, daily life without actually employing, the mathematical techniques of control, but we do it simply because by manipulating the parameters that we have, the actuators that we are allowed to access and to act on, we are testing what is the sensitivity of the model, and in this way we are being able to, say, modify the dynamics of the system. So this is typically what happens, right? So as I said, this is a particular example. I show you just a MATLAB simulation, right? We are learning what is the behavior of this system. We don't do control. Okay, fine, we don't do control, but we want to learn how the system behaves. So I take this parameter theta, and first I make it very small. I know when I am making this parameter theta very small, the one population is favorized, right? Because most of the nonlinearity is positive, is pushing towards one. So in that case, you see that even if here I take a population which is, in a universe of zeros, there is a very minority population of ones, which is just represented by this very thin column, right, representing the characteristic function of a very thin interval, right? Even if you put this very minority population surrounded by a population of zeros, it's a very narrow minority. But if the parameter theta is small enough so that the policies in order to enhance the population of ones is strong enough, then you see in the picture on the right how this characteristic function in red starts propagating, widening, right, through the generation of the two traveling waves, one traveling to the left and the other one traveling to the right, right? So this is a typical example where not only the population of ones being a minority persists, but it gets wider and wider and wider, right? By the contrary, if out of the same population, very narrow, you will rather embed this population in a, say, context in which, the one population is not favorized, and this occurs when the parameter theta is closer to 1, like 0.7, in which case most of the nonlinearity is negative. This means that everyone has a strong pressure to go towards 0 and not to remain at the level 1. Then you will see immediately how this population of ones, right, that was the same as before, this time will shrink due to the effect of the dissipativity of the diffusion plus the dissipativity of the nonlinearity that accumulate, and then will have the tendency to disappear, right? And these are the kind of results that, in order to explain the general, say, propagation properties of this system, that were proved in these, say, pioneering articles in the 70s, right? So they said, for instance, that not only traveling waves exist, but in fact, solutions that departing from an initial datum are simply compatible with the asymptotic limits at minus infinity and plus infinity of the traveling wave, they will eventually be attracted, right? And this was the basis of our first result on the control of this system. This was published in a joint paper with Emmanuel Troella in Paris 6 and Yamin Su. That was a joint postdoc student. I think this was a publication back 2 years ago in 2018, right? And we proved that based on these very properties that were already published in these pioneering articles in the 70s, just by making a bang, switching game on the parameter theta, right? You can regulate a given, say, initial configuration to reach asymptotically the given profile of a traveling wave solution, right? So that was the first result in our, say, understanding of this model from a control theoretical perspective. Now, of course, this is not hard to do when you have a very good understanding of the dynamical systems properties of the system, as it happens in this case, and how it depends on the parameters, that are available here, for us. In this case, the parameter theta, the early threshold parameter. But oftentimes when you are dealing with more complicated system, this is not something you can do analytically. So very often you will do it numerically, right? So how do you formulate these kind of problems from a numerical perspective, right? Assume you are not able to handle it analytically. What you will do if you really wanted to regulate this population, control this population? Well, this is the way you formulate it from a, say, numerical control perspective, right? You will say, okay, what is the situation? The situation is that we have here the reaction diffusion model. Now, the Ali threshold parameter theta is something that I am allowed to regulate, right? Because, for instance, a long time I can develop different, say, policies of gender or minority balance, right? So that I will favorize one population or the other a long time through certain incentives, right? The initial datum y0 is given, right? So in particular, if I fix a given policy theta, this will lead to a dynamics, right? But in this case, as I said, I am allowed to regulate the value of the parameter theta, which is a control, and this is actually the action that will allow me to modify the dynamics in a given specific direction. For instance, if my target was to drive this population at a given time window that normally I will also establish, right? How much time I am giving myself in order to reach a given, a given goal, right? Then given the time window, if the objective is to drive this population to a given profile, like the one capital U corresponding to the traveling wave solution, then the problem will be formulated simply as a simple least square problem, right? In which the goal will be to choose the value of the parameter theta as a function of t, so that the distance of the solution y to the target u is minimized, right? Okay, so these problems, although they look simple, they can be quite complicated, in particular because even if in the functional you see this quadratic distance between the state and the target, the problem is not convex, right? Because there is a nonlinear dependence of the solution y on the parameter theta, right? So this is a non-convex problem. So the search of the minimizer is something that can be complicated also from a computational perspective. And actually, this problem can very soon face, the phantom of the difficulty of the course of the dimensionality, right? And actually, in order to be able to develop successful computational tools to solve these problems, oftentimes you need to use a two-scale approach, right? You will need, say, basically, this is something you as experts in dynamical systems, you will understand it very well. You will use a small mesh size, step size, in order to produce a very fine and accurate approximation of the dynamics of the solution, right? But for the computation of the control, you will use a coarser size, because the switch in the policy you will adopt is normally done in much longer time intervals. Actually, and in this way, we reproduced the numerical simulations in this context, and we could see that the result proved, based on the classical stability properties of the traveling wave solutions using band controls, could be recomputed using also numerical, say, techniques, right? Okay, so what have we seen so far? We have seen that in modeling of biological and sociological problems, oftentimes reaction diffusion problems with bistable nonlinearities are a classical tool. They can be modified in order to deal with nonlinear diffusion, heterogeneities, multidimensional problems, boundary data, and so on. So this was just a very basic model in order to illustrate the main ideas. We have seen also that we have a quite reasonable understanding of what is the asymptotic behavior of these solutions, that one of the main properties is that traveling wave solutions arise, and this explains in particular, for instance, the propagation of, say, social opinion, right, which has, for instance, a great impact on, the switching on governments, the regimes in democratic countries, right? And that actually one of the key ingredients on, the determination of these possible dynamics is the value of the Ali threshold. And we have also shown that even if you are not an expert in control theory, by regulating this Ali threshold, you can make these traveling wave solutions to switch the orientation from left to right or vice versa, and in this way, be able to regulate the dynamics in relatively long time horizons, right? Okay. Unfortunately, there are situations where you cannot really, modify the Ali threshold. I mean, you don't have really access to, affect the way the dynamics is occurring. Or if you have, maybe, the scale of time in which you are able to, to influence the dynamics is not really the one you are interested on, right? So, for instance, I mean, if you are, you are running so I don't know, a semester program in a given topic, well, you have one semester, you don't have 10 years to do it, right? So if you don't have enough time in order to keep a given policy, it could well be that even if the policy is the correct one, you will not have time to see the impact you were expecting, right? Now, when you think in terms of population dynamics, I mean, it's very easy to visualize that a substantial source of change on, the behavior of population is, emigration and immigration. And when you think on how you model this, you will say, well, when this occurs, right, this is happening in a country where the laws don't change, the regime is the same, the constitution is the same, schools are behaving equally, right? The daily life is regulated by the same, say, civic rules, right? So theta is independent of time. Theta is given. Theta is not a control parameter, but there is inflow and outflow of population through the boundaries. This corresponds to this other situation that we analyzed in a second paper in collaboration with Pujol and Trela, was published last year in the journal Nonlinearity, in which the control is being applied through the boundary. This is another scenario. In this case now, theta is fixed. You cannot touch the Ali threshold. You are just regulating the value of the population on the boundary. So basically you are saying, okay, I am allowing this class of immigrants to come in, and on the other hand, I am enhancing, this other category of people to go out, right? So and then you will see, for instance, how, some countries are developing policies in order to attract talent, attract scientists. So they will see, scientists incoming. Some other countries, need workers to civil work, for instance. Then they will bring a different, say, category of immigrants. And this is what you see through these boundary controls. U on the left, say, V on the right. The question then we consider was, can we control, the distribution of population through this boundary game, even if, this Ali threshold parameter is fixed? Okay, so in this case, we took theta less than 1/2. And then we said, let's see what happens. So assume, for instance, I want to, I am in a situation with theta is less than 1/2. I am living in a country of length capital L. So now the space interval is finite, goes from 0 to L, right? And I apply zero policy on the boundary, right? So I say, I really enhance the, on the borders of this country, the population to be zero, either because it was zero, or if it was not zero, because I let people with, say, Y = 0 gene to come in, right? What happens then? Well, if you run this simulation, for instance, in this case, we started with an initial datum that was very close to 1, a population which is close to 1. If you fix the boundary to be 0, right, then you see that due to the diffusion effect, which is making this zero value from the boundary to penetrate inside the domain in combination with the nonlinearity, you see how the population goes exponentially down to zero, right? So this is a case where you say, well, this is like at home, right? I'm at home, no heating at home, zero temperature outside, you know, it's freezing outside. So eventually, if I don't have any heating device at home, this zero temperature from outside will penetrate within the room, and the temperature will start to go down and down and down, right? This is what this simulation is showing. And okay, that seems natural. Now, we took the same simulation in a longer domain. Now, rather than being a domain of length 0, 7, I took a domain 0, 11. So the room is a bit larger. And when we ran the simulation, we observed that rather than, you know, the solution going down to 0, the solution seemed to exhibit the convergence to this kind of, say, sinusoidal wave, right? And we said, well, you know, maybe simply because the diffusion process, the dissipativity now here is slower because the domain is bigger. Maybe we let time to be larger, then we will see that this solution actually goes down to 0. But in fact, it didn't. We kept this simulation very long, and we have the impression that the dynamics is going to this kind of steady state solution. Then we started to look a bit more on the existing literature on reaction diffusion problems, and we found that, again, you know, in the 70s there was a complete theory developed for one-dimensional, say, reaction diffusion problems, in which basically there is a famous paper of Matano in particular on this, where, you know, basically, you know, it is well known, if you have bounded solutions of reaction diffusion problems in 1D, you know, the solutions have the tendency to go to steady state solutions, right? So then we wonder, well, if the solution is tending to a steady state solution, why it doesn't go to 0? I did everything, right? I have put boundary conditions equal 0 on the boundary. So everything was done so that the solution goes down to 0. Why it doesn't go to 0? And then we said, let's analyze a steady state. In particular, there is I mean, this was again very active in the 70s by the classical works of Ambrosetti, Rabinovich, critical point theory, the calculus of variation, in order to analyze, say, the existence of solutions of semilinear partial differential equations of elliptic type using the minimization and critical point techniques, right? And then in this particular case, you see that the functional we have to minimize or to find the critical points of is very simple. It's just this functional in red here down, where you have the Dirichlet integral 1/2 of the integral of yx squared minus the term contributed by the nonlinearity, right? For which, of course, 0 will be a critical point, right? And you wonder why, you know, these other guys are isers, right? And why, in particular, the length of the domain capital omega, length large, can have an impact on the possible emergence of this new attractor that could very likely be, say, a steady state solution. And it's actually by looking to this problem that you realize that indeed, right, when L is large, the first eigenvalue of the Laplacian, which is pi squared divided by L squared, is very small. Then the quadratic term in this functional J has the tendency to be less and less and less positive. And then the second term on this integral, which comes with a negative sign, starts being, say, more dominant. And eventually the global minimum of this functional becomes negative. So that indeed, it is true that there is a bifurcation on the behavior of this minimization problem, in the sense that when the size of the domain is small enough, the global minimizer is 0, but when the size of the domain is large enough, the minimizer is non-trivial, the functional takes the negative values and the minimizer is non-trivial. And this is what explains that there is this switching or this swapping in the dynamics of this system, even with this simple boundary control in which you freeze the boundary to 0. You see how in some cases when the domain is small, this is successful enough to bring down the population to 0, while when the domain is large enough, there is still the possibility that this generates some non-trivial dynamics inside, okay? And this is something that once you discover that is related to the possible existence of non-trivial solutions, you can understand in general using the techniques of nonlinear partial differential equations. And in this particular case, by using tools of phase plane analysis, because the steady state solutions are solutions of a second order ODE, right? Last summer, not this year, but the previous year, we were together with Dominic Ruiz, that I mentioned before. We were giving a summer course on this topic in Chengdu, in Sichuan University in China. There were plenty of students there, and we were explaining a little bit of, the basics of these reaction diffusion problems, dynamics, control, the numerics, and in particular, we were interested on trying to convince people that the size of the domain could matter. And I said to Dominic, well, Dominic, it will be good to find a good, say, paper applied oriented that, somehow allows to justify all we are saying. And Dominic found these articles, right, in which they are analyzing the population of pandas. As you know, Sichuan province in China is the region in which, the biggest population of pandas, the forest with the biggest population of pandas are located. And this paper, it was precisely discussing this topic. Pandas can survive if the forest, they are allocated for is large enough, but you will not be able to, to grow pandas in the gardening of your apartment, for instance, right? So large regions favorize the emergence of non-trivial steady configurations, which in particular allow for the survival of a non-trivial species, right? Even if the, say, borders are hostile and are repulsive with respect to this population. And this is something that, in the beginning I said that our original motivation to this topic was, say, bilingualism, and this is what explains that, even in this age of globalization, languages that are not minority language but are sufficiently represented survive, right? Despite of the pressure of, the globalization tendency, so that we all adopt majority languages. But on the other hand, languages like the Basque language in Basque country, which is a minority language, they are in the risk of, say, disappearing because the country is too small, the population of, say, native speakers is not sufficient to, to resist, right, to persist under the action of these, say, exterior, say, global languages, and this will be a case where rather the language has the tendency to disappear, okay? This is the work we have done. We have continued working in this area, as I mentioned, with Dominic Ruiz Ballet, and also with Idris Mafari, who recently got his PhD in the University Paris 6, and he's now a postdoc in Vienna, an expert on, say, these reaction diffusion models arising from, say, biological sciences. In particular, we have analyzed these gen flow models in which you have a cascade of reaction diffusion equations. In this lecture, I have discussed just one single reaction diffusion equation, but oftentimes in sociological and biological processes, there is a cascade of reaction diffusion equations, and the reason is very easy to understand and is represented in these chain flow models, in which you have a population which is diffusing and emigrating and traveling because of very basic, say, reasons, like in the search of resources, people looking for jobs, people escaping wars, right? Just looking for peaceful lands where they could, say, live and grow, right, and make their families grow, right? So this is kind of a macroscopic diffusion and propagation effect. And underneath, right, you have the genes that this population are carrying. And when I'm talking about genes, it could be also some cultural traits or cultural traditions, right? Multilingualism, religions, and so on, that they carry. And this is driven by a second reaction diffusion equation that is subordinated to the first one. Of course, these models are harder to handle because they are more complex, but to a large extent, the techniques I have shown you here can be employed to do it, right? When you analyze these models, you realize that the techniques you have to implement to control these models push you to use controls that are quite complex. And actually, once you develop them from an analytical perspective, you can wonder whether this kind of switching and oscillating controls are really necessary. It's very nice to see that by doing numerical tests, you can indeed realize that oftentimes the needed control dynamics is quite complex, is not so intuitive, and this was in particular confirmed by our simulations, that in this very particular case of one-dimensional reaction diffusion equations can be implemented using this, say, again, open access software, IPOPT, right? Interior Penalty Optimization. This is a software that was developed 30 years back in Carnegie Mellon, and you can download for free. This was, I think, originated in the Department of Chemical Engineering in Carnegie Mellon. I mean, this is an optimization software that was developed in order to regulate the dynamics of large, say, chemical reaction systems modeled through cascades of ordinary differential equations. But once the software, is accessible and is accessible for everyone, you can implement it in order to, to optimize all kind of dynamics, and in particular a discretized version of these reaction diffusion models, right? Okay, so some conclusions on this before I just switch to some last comments on machine learning. That is a topic that is somehow hidden on this, right? And this picture here is a very good, say, motivation to transit to this other unexpected or hidden, say, dimension of these problems, right? You see, the difficulty of dealing with this nonlinear dynamics and control is that often, the nonlinearity of these models and the large dimensionality, so reaction diffusion models, they live in infinite dimensional, say, Hilbert spaces, right? We are living with problems in which the landscape of the solutions we are handling, both in the dynamical system context and also in the steady state context, is very complicated. How the solutions depend on the various parameters you are allowed to modify in the system, either the Ali threshold or the boundary condition, is extremely oscillatory and nonlinear. So it's very hard to figure out, right? In particular, when you try to minimize in order to find some optimal strategy, you realize the functional you are optimizer are far from being convex, as the one represented by this kind of polygonal oscillatory landscape. Is very far from being complex, right? Convex. This is why it's very hard to have an intuition, right? And this is why our work has always been try to combine analytical understanding with numerical simulation that oftentimes can be a very, illuminating tool in order to guess what are the possible new strategies, right? And when you think on this, you realize that this is to a large extent what nowadays we are doing in the context of machine learning, right? Just to conclude, a few comments on this, right? So, of course, as it happens always, the origin of a given topic, as the one of machine learning, deep learning, neural networks, residual neural networks, and so on, is not unique, right? It often comes from inputs coming from different areas. If you think on this topic from the perspective of an analyst, as we are mathematical analysts after all, that got interested on PDEs and then numerics and then control, and through applications on this topic of reaction diffusion models in particular, right? But also other kind of variants in different contexts of partial differential equations. From our perspective on analysis, probably the origin of this machine learning topic will be, this paper, for instance, by Sivenko, where he says, the universal approximation theorem, which is very close to actually the theorem by Lebesgue saying that every function in the context of measure theory can be approximated by simple functions. He reformulated that in terms of linear combinations of sigmoids through, say, different, parameters that not only allow to amplify, but also to scale and to translate, right? When you look to this formula, the sum of alpha j sigma of yj x plus theta j, you see that there is the same basis function sigma, which is translated with theta, which is dilated with the parameter y, and then finally amplified with the parameter theta. There are three parameters through which you cook a combination that allows you to reproduce this kind of, neural network with one layer, but a big, width that allows to approximate any kind of nonlinear function, right? And this nowadays is one of the key tools in order to, for instance, implement, classification methodologies, automatic classification methodologies that we all understand and that are so relevant, in particular in internet. Whenever you open your search engine and you put the name of a person and you want to see the corresponding images, you expect this algorithm to be accurate, maybe not 100% accurate, but to a large extent precise, so that whenever you put a name on it, you will find the images corresponding to this person, and maybe it's relative, but not to other people that are not associated to this name, right? So how is this related to dynamical systems, control, and the kind of topic I was developing so far? Well, there is a clear link, right? So people realize that this Sivenko methodology, in which you can, approximate any function, right? If you are able to approximate any function, then you are also able to classify data, because you can build functions that are taking, the data from a given color to the left, those of the other color to the right. This is like generating a given, distribution function that is able to split population into two. These segregation functions, as the one that we have seen in our lecture on the traveling wave profiles, right? And actually, people have realized that this was, in particular, a contribution by Wayne and Ian, collaborators, that started in year 17, right? A few years ago, 3 years ago, actually, that, if you move from the original framework of Sivenko to what is called the residual neural networks, in which rather than taking a very large, width of your neural network, you keep the width fixed, but you augment the depth by iterating this kind of sigmoid nonlinear process, once and again, then you generate, say, discrete dynamical systems that you can also interpret in a continuous manner. And then by using the same kind of methodologies as the one I have been presenting in my previous part related to, say, the models in mathematical biology, you can succeed on, say, generating algorithms that are also able to classify data. And just to conclude, let me show you this video. I think Boumediene has seen this video because this is part of a lecture I gave on the very nice workshop he organized recently in the Fields Institute, the Zoom workshop, the Zoom colloquium, right? You see in this picture here in the middle, right? You see like a soccer field, and you see two teams, right? The team of the red players and the team of the blue players, right? And you would like to develop an algorithm so that, every player understands that it has to take, he or she has to take the half of the field that corresponds to the color of your t-shirt. So in particular, I would like the red t-shirts to occupy the space on the left and the blue t-shirts to rather move to the right? So by using these techniques in which, you identify the neural network with a dynamical system and you implement the same methodologies we have developed before of control of dynamical systems implemented in here, you see how the algorithm works, and indeed, efficiently, you are able to classify data so that the red data move to the left and the blue data move to the right. So once you see this picture, it's not so hard to believe that there is a clear connection between machine learning and in particular social behavior, right? Because you could identify these points also with individuals with different, say, cultural traits, trying to be moving to a school or another, or to a neighborhood or another, or to choose a different restaurant depending on their, of their, say, culinary taste, right? And this is where I would like to stop. There is a big field in which very challenging applications in social and biological sciences require of new analytical tools and new numerical tools that are very much connected to the control of dynamical systems. And surprisingly or not, depends on your cultural origin from a mathematical perspective, this is very much related also to the kind of problems you can solve using machine learning techniques, but also to the type of problems that from a mathematical analysis perspective you will encounter if you try to understand what are, say, the ingredients that make the tools of, say, machine learning to be so efficient for problems that, are hard to deal for other, say, more classical techniques or analysis or numerical analysis. Thank you for your attention. And thank you again, Boumediene, for the occasion you have given me to talk in this forum.
Yeah, thank you very much. Thank you. Any questions? Yeah, so I had two questions. So first one is about did you apply this to models of pandemics, like the first part, where the corona, like how it spreads in?
Well, so you see, Boumediene, for corona here in Erlangen, in Friedrich Alexander University, where I am now, there has been a lot of activity in this area, and colleagues have been doing very successful research for the corona pandemics and the regulation and the control, right? Not only in our team, but also in others. But I think, I mean, the dynamics is extremely nonlinear, right? So what we say qualitatively is correct, right? So actually, you know, when people say that we go to confinement, what we are doing? We are changing the parameter theta. What is confinement? Confinement is either change the parameter theta or reduce the diffusivity, because with less social contact, there is less, say, propagation of the virus. So when we say we do, say, social isolation, confinement, we are simply putting a barrier to the, say, the virus to propagate. This is like precisely doing what we are saying here, right? Either regulating the parameter theta or regulating the diffusivity, or both simultaneously, right? But you see, mathematics agree on the fact that in the absence of vaccines, in order to, you know, diminish the propagation of the pandemics, basically the only thing you can do is to tune these parameters, right? Now, beyond these, say, qualitative results that you can confirm in practical applications, you know, a complete understanding of the propagation of the virus, I think is out of reach, right? So in particular, we have seen that, you know, the globalization aspect is playing against, you know, the control of the pandemics, right? So even in countries or in towns or in regions where the pandemic was low, you know, the numbers increased again, and this is mainly due to the, you know, to the transport of people, to traveling and long, you know, distance interactions through, say, international traveling. And well, I think nobody has a global simulator, right? It would be great to have it, but it will certainly be something that is beyond, I think, the computing capabilities of anyone, right? So this is why I think this pandemic is being driven to a large extent by data and statistics, right? Yeah, thresholds that tell us when we should increase the level of, you know, isolation or confinement, so to make sure, you know, given thresholds are not, you know, crossed over, right?
Yeah, just so that maybe this can be used for like local lockdowns or these kind of things, where instead of looking at the global lockdown, like here in the UK, they're doing like local lockdowns, and then you have like different.
Yeah, I think you are right. I mean, you know, the model, of course, confirms that, you know, lockdowns, I mean, are needed, are necessary. Now, in practice, are these decisions made based on partial differential equations of this type? I don't think so, right? And can partial differential equations of this type add precision to these lockdowns? I'm not sure, right? Because we will need to know a lot about the model, right? In particular here, I am taking a very simple diffusion model, right? But what is really the diffusion process corresponding to a city, a region, a country, in which, you know, in the city of London, you know, millions of people are commuting in the metro every day. What is the diffusion operator corresponding to this?
Yeah,
I think there is no way of, through such simplified models, get to an accurate description of such a complicated propagation phenomena, right?
Yeah, makes sense. Yeah, okay. So there's also another question about the last part, about the ResNet part.
Yeah.
I was wondering if there, I mean, there is a kind of paper that I started looking at recently where it shows that there's an impact of the activation function on deep neural networks training, and then by changing the activation function, you may have a chaotic behavior or this kind of things. I was wondering if there is a way to. It's like you say, like remember like this inverse optimality problems, where in that case we would be looking at how to choose the activation function such that we have some some qualitative behavior for the neural networks. So yeah, so instead of looking at your data, I mean, here we would be looking at what are the best activation functions.
Right. That's, I mean, of course, that's even harder, right? So you see, because when you look at this, maybe at this point is where we see better, as you said. I mean, from a dynamical system perspective, we say, okay, I have a dynamical system x dot equals sigma wx plus b. And then if you are a control theory, you will say, okay, I will use then W and B as control parameters, as the Ali threshold parameter or the boundary condition in this reaction diffusion problem. But normally you do it under the assumption that the dynamics is governed by a given sigma, right? That could be this exponential sigmoid here, or this ReLU, say, piecewise linear function. Now, analyzing the sensitivity with respect to sigma, of course, is much harder, right?
Yes.
You can differentiate the model with respect to sigma, but then this is a second level of difficulty on this problem, right?
Yeah. Exactly.
We didn't really do that. I mean, what we have done so far in this context is, for a given sigma, we try to explain that control techniques allow to understand the performance of the process, right? But that's a very good point, right? To really go more deeply into this and identify what could be the optimal sigmoid for a given task, that's even more challenging, I will say, right? You are thinking now on which articles are you referring to, Boumediene?
Yeah, so it's, let me share my screen to show you which page.
Yeah.
Yeah, that one. Do you see it? Do you see the paper? I can't hear you actually. Yeah, sorry.
No, I was saying that I don't know this paper, but that sounds to be, I mean, this is also a very interesting topic, right? So
yeah, it seems to work in a nice direction.
Of the activation function, right?
Yeah, so I'll send it to you by email. Yeah.
Yeah. Okay, that's very nice. This is not an easy topic, right?
No, it's not an easy topic, especially that in this paper they show that actually even the qualitative behavior of the network changes, like just ReLU function or sigmoid or this kind. I mean, you may reach the chaotic behavior, and yeah, no, this is definitely not an easy topic.
Yeah, this is subtle, right? Because you see, if I go back to my slide, so what I said, to a large extent, right? What I said, in our case, even in this simpler, say, reaction diffusion problem, as I said, all we are saying is quite qualitative, right? It will not depend really on whether this nonlinearity is cubic or not, right?
Yeah.
We are describing phenomena that are, say, generically true for this kind of, say, bias-stable nonlinearity, right?
Yeah.
If you will ask me now, can you really be more precise and explain with more detail how, the dynamical properties or the control properties of this system depends on the fine tuning of this nonlinearity? This is a second level of difficulty, definitely, right? And this is not something we have done. Yeah, I don't know. That will be challenging, right?
Yeah, I see it as challenging problems. So even that paper, I can send it to you, and it may be nice to look
you
at.
see, normally control theory, but even in linear systems, right? So you look to these classical control theoretical results for linear systems. They are based on the Kalman rank condition. For instance, you have a dynamics driven by an operator A, a control operator B, and then you compute the rank of A, B, and some consecutive, say, powers of enchainment of powers of A and B. And then when the rank is full, you say the system is controllable. Now, saying when changing the parameters of the system make the dynamics more controllable or less controllable is not so easy.
Yeah.
And in the nonlinear context, this will be even harder, right?
Yeah. I was thinking about this stuff of, remember like Randy Freeman and Kokotovich about inverse optimality.
Right,
Yeah.
right,
So
right.
I was thinking about something like this, like an inverse optimal control problem. So instead of, because people like you mentioned, like when an are looking from an optimal control point of view, but what about doing the inverse optimality where you specify your dynamics and then you try to find the controller in such a way that you have the right performance? Yeah.
Are you interested on this, Boumediene?
Yeah, we can. I think it seems like a nice topic. Yeah.
Definitely. Yeah, we can have a look. Yeah, but
Yeah,
that's
sure. That would be nice. Yeah.
that's not one of the easiest, I would say. Right?
Yeah, no, definitely. Yeah. I agree that it's not an easy thing. It just just through our talk. I mean, it has been a while. I did not do a work on control theory, but this like reminded me.
Definitely.
Yeah.
That's an interesting.
Actually, you wrote Sergey Andrew. What was that? More on feed forward. Yeah, I think it's a more of feed forward network. All right, but that's the paper I was referring to. Just put it on the chat.
Okay.
Yeah, but you can talk. I mean, Sergey, if you want. I mean, it's an open forum, somehow. So it's,
I see the chat.
Hello.
Yeah.
Well, yeah. The thing is that with ResNets, like if you suppose that the skip connection is like small, then approximated in SOD is kind of the activation function does not play a role. I think Shauli did a paper in that and tried to like give the minimal things that this skip connection should have in order to generate whatever function you want. But I think that stability and all of that with forward is super difficult, and actually are not used a lot in very deep neural networks because of that, because of chaotic behavior. But with ResNets, I guess everything is quite easier. So the activation function, it's okay, always important, but not that much. In the case Enrique was talking about, I think.
So this paper that you mentioned in this, I see there are two papers on the chat. These papers don't refer to ResNets, you say?
No, I don't think so. Well, maybe they can, but the thing is that since ResNets can be made out of multi-layer perceptrons, of course it applies. But in principle, the chaotic behavior is more into studying feed-forward networks rather than ResNets, I guess.
I see. Yeah, that makes sense, right? So the way, at least the way we address this is quite, say, smooth in the sense that we say we take this nonlinear dynamical system. The fact that sigma is a ReLU already introduces some difficulties because sigma is not differentiable, right? And therefore, from a control theoretical perspective, you have to be more careful because you cannot simply differentiate the system, linearize the system in a classical manner. But despite of this, in our analysis, we see that the controllability properties that the system exhibits don't seem to depend so much on whether sigma is, say, the smooth arc tangent sigmoid or the ReLU, right? Yeah.
Yeah, makes sense.
Yeah, because this is within a very specific class of dynamical systems in which, you know, the sigmoid behavior is sufficiently generic so to guarantee the splitting of the space into, say, on two differentiated parts, and then the choice of the regulating parameters W for the compression and B for the translation are able to manage, say, the rest, right? So we don't, I mean, our analysis is not precise enough to discriminate within the different sigmas, but we don't see any significant change on the qualitative behavior, right? Yeah. But definitely in practice, I'm sure the efficiency of some sigmas will be higher than the others, right? But again, this is an optimization problem. And in this time, optimizing within the sigmas, which is even more difficult, right?
Yeah. All right. Any other questions? Yeah, okay. Yes, so let's thank the speaker again for the nice talk.
Okay, so thank you, Boumediene. I will be happy to, I mean, we are here, so we'll be happy to interact with any of you. Don't hesitate to send us an email and keep in touch, okay?
Yeah, Take care. Stay safe.
Okay, you too. Bye-bye. Ciao.